Can you hear me?
Yes, sir.
Where will we receive the links for these classes? Okay. So these recorded sessions are in YouTube. So I will share with you. Let me share with you my YouTube channel's link. So you can find it in the channel. So just give me a moment. So here is the channel. In this channel, there are multiple playlists. So you have to go to the playlist called Fundamental Algorithms 2025. There all the videos will be available. All right. So let us get started. So this is week 2. So we are in week 2. So what is the idea? So this is going to be a live interactive session where we will discuss some sample problems from the content of week 2. Specifically, we'll look at the assignment 2 questions from the previous offering of this course. All right. So let me, uh, so there are five, oh no, sorry, there are 10 questions. So we'll start with the first one. So, but before that, if, do you have any doubts or any comments, anything? Oops, sorry. From the previous session, from the previous week, if you have any doubts, you can ask.
Hello, sir.
Yes.
So I have a doubt. In the video, Professor told that in master theorem, for example, if
Okay.
Pn is equal to A to N by B.
Mm-hmm.
So, sir, where it was, sir said it as A has to be greater than 1. But in the latest Foreman edition, some professors have taught that A can be greater than B also.
Okay. So, so what is the lower bound on A? That is the question you are asking.
Yes, sir, in master theorem.
So is this the master theorem you are referring to?
Yes, sir.
So you are saying that this could be zero as per some source, or you said Corman, as per latest
Yes, sir,
Corman.
Foreman did.
But this is as per, is this 1 or greater than equal to 1? I don't know. Okay. So let me just give me a few minutes. Let me find it out what is written in Corman. I can see that A is greater than equal to 1 and B is greater than 1 are the constants. So which edition of Corman you are looking at?
So I don't know exactly. I think third edition.
Third edition. Okay. So I think the latest one is fourth edition. Just give me a moment. I'm checking fourth edition as well. Okay, so it is saying that the master method is this where A is greater than 0 and B is greater than 1. So you are right. So in the fourth edition, they are saying that A is greater than 0. See, the thing is, so what I think is the following. So the, for the master method, we have three cases. We compare two things. We compare whether log to the base BA is greater than or equal to or less than C. So C is this exponent, right? This is what we check. So now Corman is saying that A is greater than 0 and B is greater than 1. This is as per Corman. So for this quantity to be valid, the base of log, which is B, that is B, should definitely be greater than 0, greater than 1. And if you take log of a number, so log to the base BA is asking that for which x b to the power x is equal to a. So you know for a fact that since b is greater than or equal to 1, b to the power any x, okay, b to the power any x is definitely greater than 0. So b to the power 0 is 1, b to the power something positive is greater than 1, but b to the power something negative, that is also greater than 0. So you know that a cannot be less than 0. That's why, just to ensure sanity here, they have taken a greater than 0. So in my opinion, whatever Corman is writing is fine. As per the definition of log, for this expression to be valid, uh, we should have no issues assuming that b is greater than 1 and a is greater than 0. So I will, this is my explanation for why this is right. Did you understand what I said?
Yes, sir.
Okay. So have any further questions? Okay, so there is a message. Ayush is saying that I joined the course yesterday, but I got a notification that today's the last date for submission of assignment 1 and 2. Is it possible to do it later? Okay, so I am teaching assistant for this course. So my responsibility in this course is limited to conducting these problem solving sessions and interacting with you, clearing your doubts. So as far as changing the last date of submission of assignments or examinations are concerned, I have no say on it. So you have to write an email or you have to put it in the Q&A. So there is a Q&A section in the course web page. You will see there is a Q&A section. So there you can ask this question that can we delay the assignment deadline. So then the concerned person will be able to make the necessary changes. So I have no say on it. Okay. So is there any other queries? So we'll start with the first question of the day. So this is question 1 for you. Which of the following sorting techniques is stable? So Gahan is saying counting sort. So first of all, what is a stable sorting technique? So we have seen what is quick sort. We have seen what is counting sort. I think heap sort is also discussed. I don't remember. Selection sort, I think we have seen. So a stable sorting algorithm is an algorithm that maintains the relative order of the elements with equal values. Okay. So for example, suppose you have, let us say, this is a set of numbers that you want to sort. So there are two occurrences of 4. This is the first occurrence, this is the second occurrence. So for identification, let us say this is the first 4 and this is the second 4. This is not power, this is just for identification. So the algorithm should output something like this, that the relative ordering of the uh, elements with same values is maintained in the output. So that kind of an algorithm will be called a stable sorting algorithm. So you have seen what is counting sort. So counting sort maintains this relative ordering of the elements of equal value. Therefore, counting sort is a stable sorting technique. So let us recall counting sort for. So let's bring this. I'll do it here only. So let's take this only. So for example, if this is our, please define stable algorithm again. Okay, so let's take an example. So stable sorting algorithm. So what is a stable sorting algorithm? So the algorithm must maintain what? The relative ordering of the elements having equal value. So for example, suppose the input is an array A and you have these numbers. What did I write? 4, 2, 3, 4, 1. So 4, 2, 3, 4, 1. This is your input. So what does the sorting algorithm do? So it generates A dash, which has the numbers sorted. So after sorting, this is the output you will get in increasing order. The numbers are in increasing order 1, 2, 3, 4, 4. Okay, so during the processing, what will what are the two possibilities? So for example, for identification, say this is the first one in the input. This is the first 4 and this second 4. There are two elements with equal value. So this is one copy, this is another copy. So let us say this is the first copy, we denote it as 4 1, and this is another copy that we denote it as 4 2. So if you maintain that 4 1 appears before 4 2, then the relative ordering is maintained. If the algorithm can ensure that, then we say that the algorithm is stable. Okay. Do you understand stable, Nitish? Thank you, Nitish. So now let us look at, so if you give this array A to the counting sort algorithm, then what will happen? So let us see what will happen. So it will first generate an array. So the array has size. It is for the counting purpose. Let us call it the count array. It has size, the range of the numbers. So the numbers are within the range 1, 2, 3, 4. So there are 4 elements in the array. So first it checks that what is the first number? It is 4. So it counts that, okay, in there is one occurrence of 4. Then it checks the second number, it's 2. So it goes to index 2 and says there is one occurrence of 2. Then it checks the third number, it is 3. It goes to index 3, there is one occurrence of 3. Again, it finds that there's another 4. Then it updates the number of occurrences of 4. It says, okay, now I have seen 2 occurrences of 4. And then it sees 1. So it says, okay, so 1 has appeared once. So this is what it does. So it knows that there are 2 occurrences of 4. But when it will output the occurrences in the same relative ordering. The first uh, 4 that it has seen, it will show that first, followed by the second 4. So there is some prefix sum array which we use to show the output, which we have seen in the videos. So therefore, the counting sort algorithm is able to maintain the relative ordering of the elements having equal value. Therefore, it's a stable sorting algorithm. Okay. Is there any questions? Any doubts? So just give me a minute. There's somebody at the door. Okay, so I think uh, I explained the first question. If there is any doubt, you can ask me. Otherwise, we'll move to the second one. The counter is added to 5. The counter is added to 5 in the last slot. So the last input of 4 will be placed at the 5th position of the output array. All right. So the last input 4 will be at the 5th position. That is true. So the first input will be at the 4th position. So I agree with you. So this is question 2 for you. So I'll give you a minute to think about it. Okay, so somebody has answered 15. So you have seen what is a hash table. So there are 157 slots in the hash table. So how does it look? So let us say this is the hash table. There are 157 slots. So let us say this is the 0th slot, this is the second, first one, this is second one, and so on. Okay, so the last slot is 156. So that the total hash table size is 157. Okay. So now the key of 172 will be placed where? So what is the place of 172? What is h of 172? So we take the remainder of 172 when divided by the size of the hash table. So if you divide 172 by 157, so you get 1 with remainder 15. So remainder is 15. That is the point. So forget this. The remainder is 15, isn't it? So therefore, at position 15, wherever 15 is, 172 will be placed. Is there any doubt on this? Okay, so Gahan has no doubt. Anybody else? So this is question 3. I'll give you a minute uh, to read the question and think about it. So Gahan is saying 5. Alok is saying 0. Okay. So we have seen counting sort before. So what did you see? So we saw this input was like this. What was input? 42341. Okay. So we saw that if the input is like this, then what we did was we just created one array which has range, which is size equal to the range. Range means how many numbers are there. So here numbers are from 0 to 4. So the array size is 4. and then we counted. So when we saw 4, we placed a 1 here. When we saw 2, we placed a 1 here. We saw 3, placed a 1 here. Saw 4 again, so we said, okay, so now we have to update the count of 4. So we said we'll remove 1 and place 2 here. And then we saw a 1, so we put a 1. So we are just counting. We're just going to each input element of the array, and we are updating this count array. That's what we did. All right. So what are we going to do here? So here, what is the range of elements? So range is between 9 to 22. Okay, so we'll take an array. So the first part of the array, there is nothing to do. We'll start from 9, 10, 11, and so on. We have to go till 22. Oh, sorry, 28. 28 is the largest number. We have to go till 28, 27, and so on. And what are we going to do? So we are going to scan the input. So what is the first thing? 9. So at 9th position, I'm going to count 1. Second one is 7. So at 7th position, I'm going to count 1. Then there is a 13. So at 13, I'm going to count 1. I was not able to hear you. Okay, so after 13, we're looking at 28. So 28, we are going to count 1. 22 also, there is a 22 somewhere. There also, I'm going to count 1. So the question of comparison doesn't arise. We just scan. No number is getting compared with anything. What is comparison? So if you want to check whether A is less than B, that is called a comparison. So this is called comparison. So because comparison is not taking place, then the number of comparisons required to sort the array is 0. Is that fine? As the name suggests, it's counting only. It's only counting, no comparison. So here's question 4 for you. So I'll give you a minute to read the question and think about it. Yes, yes. For 42341 also, number of comparisons is 0. There is no comparison is 0. Only we count. So we scan the array and we just update how many are there. So they're counting how many elements are there. 4 has 2 occurrences. We have captured that. So this count array is capturing how many elements are there of each value. So question of comparison doesn't arise. So number of comparisons is 0. Is that fine, Nitish? Okay. So we're looking at this question 4. So it is given that there is a hash table and there are 1000 slots in the table. So the number of slots is 1000 and there is a corresponding hash function. So the key k will go to which slot of the table is given by this hash function. So h of k is this function. So where a is a number, an irrational number, root 5 minus 1 by 2. Okay. So then the key 61 is mapped to which location? So we want to calculate what is h of 61. So if you can calculate this, then we are done. So whatever is h of 61, so we'll plug in k equals to 61 in this formula. M is already known to be 1000. A is already known to be this. We have to use a calculator and we will get some value here. So whatever that value is, I don't know which one is the value, will be our answer. Okay, so I will give you a minute. You plug in the value of, so I want to calculate h of 61. So what is h of 61? This is m is 1000 and then k is 61 times a, that is root 5 minus 1 by 2. This thing mod means the fractional part. So when you say mod 1, you are just looking at the fractional part. And then you take floor. So remember, suppose you have 4 point, so I'm just giving an example, 4.3 mod 1. So that means you take the fractional part of 4.3, that is 0.3. Okay, so you have 9.44 mod 1. Then you take the fractional part, that is 0.44. Okay, so now you can do this calculation for yourself. Okay, so we have one answer. So all of you try to calculate this. Nayana Shri is also getting 700. Gahan is also getting 700. Anybody else? Anubhav has also got 700. So there is a good confidence that 700 is probably the right answer. Spandana is also getting 700. So that means this key 61 should go to that slot 700. So how many slots are there? There are 1000 slots in the hash table. This is like 999. So whatever the key is 61, that is going to the 700 slot, if our calculation is correct. Okay. So let's look at it. So I'm going to do it. So 861. So 1000 times 61 times what is root 5? Root 5 is 2.24 approximately, minus 1 by root 2 mod 1. So this thing is float. Okay. So this is like 1000. So 2.24 minus 1 is 1.24. 1.24 divided by 2. So let me write it. So 1.24 divided by 2 is 0.62. Yeah, I think I'm right. Mod 1. Take floor. So now I will just do this. So 61, 62. So this is 2. Wait. Did I make a mistake? Okay, okay, fine. 122 and 6. So 37.82. 37.82. Is this correct? Let me use a calculator instead of doing it by hand. Okay, so we have to be precise and we have to do it till one more precision value. So when I'm doing it with the calculator, I'm getting 700. So we have to take more for square root 5. We have to take a more precise value. So instead of 2.24, we have to take a more precise value. So we'll take 2.2361 minus 1. So now whatever we have, we divide that by 2. So I'll get 618. So here I will get 618. This I'm going to multiply with 61. So now I'll get 37.700. So now I will get 1000 into 37 point, oops, 7000. What is happening? Yeah, we have to take the mod also, right? So that is the reason. So take mod. So 1000. So we just take that uh, decimal part. So 0.7000. Now you multiply it with 1000. So you get 700. Yeah, so by hand, if you don't have access to a calculator, it's slightly time consuming. So is this all right? So I did it by hand so that in exam, I don't know how it will be, so that you can see all the steps. So we can move to the next question. Hence, we have to use calculator in the exam. Yes. Yeah, takes time. But if the calculator is not there, then you have to do it like this only, painstakingly. So now again, a question about counting sort. So we have already seen counting sort. What is the space complexity? Auxiliary space complexity. What is auxiliary? Let us say space complexity only of counting sort. So we know for a fact that if you, so okay, what is n? N is the size of the input array. It's the number of elements in the array that you want to sort. So I'll give you some time. there is an answer. D is correct. Alok is saying D. Let us see what others are saying. So what is the space complexity? So we have seen what is counting sort, how we have counted. So first is you have the array which is A, and I am saying that the size of the array is n. So to take the input, this is the size of the input. So you know that just to take the input itself, you need order n space. That is minimum space you need. Now you have to also count how many occurrences of each element is there. So what is the size of this count array? So what is the range of the input? So the input, the largest T is the largest number in the input array. Okay. So now you must have a count array of size which is able to count how many occurrences of the largest number is there. So the largest number, if it is capital L, you should have an array of size at least L. So here they're saying that the range of input is T. So the largest number is T. So the size of the count array is T. So the total space required is N plus T. So that is this is the correct answer. All right. Both Alok and Gahan are correct. Is there anybody else? Is there anybody who thinks that D is not the correct answer? Some other option is correct? Yes. Ramnaran, you have something to say? Mr. Ramnaran? Okay, I think by mistake he unmuted himself. So he left the conversation. I think he was embarrassed anyway. So fine. It's nothing to get embarrassed here. Let's move to the next question. So this is question number 6 for you. Again on hash table. So you have seen hash before. So I'll give you 2 minutes to think about it. So there are 9 slots in the hash table and you have to insert 9 keys. But some of the keys can get mapped to the same slot. And if that happens, then there is a collision. So if there are multiple keys, that are mapped to the same slot, then they are stored in a linked list or chain. So you have to tell that what is the maximum number of elements that are mapped to the same slot, and what is the minimum number of elements that are mapped to the same slot, and what is the average chain length. That means that is immediate. There are 9 keys, 9 slots, so the average number of elements per slot is 9 by 9, 1. So we can right away tell that either A or C is correct, because the average chain length is 9 by 9. There are 9 slots and there are 9 keys. So definitely we have either option A or option C as the correct answer. Again, so these two have also matched, so the minimum is also not a problem. So the question is, what is the maximum number of elements, keys, that can get mapped to the same slot? So how you decide A is mapped to where is using this hash function, K mod 9. Okay. So Gahan is saying option A is correct. So he's saying that out of these keys, at most 3 keys can get mapped to the same location in the hash table. So there are 9 slots in the hash table, and the hash function is K mod 9. So what are the slots in the hash table? Let's see that. So I'm drawing the hash table. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So 9 slots. So first we'll check 5 gets mapped where, in which of these slots. So how you do that? So we have to compute HK. So HK is 5. So as per the hash function, it is 5 mod 9. That means if you divide 5 by 9, what is the remainder? So it's 5. So in position 5, I will place the number 5. So now for 28. So we'll calculate H28. So that is 28 mod 5. So divide 28 by 5. Oh, sorry, not 5. 9, no? It's 9. So what is the hash function? K mod 9. So 28 mod 9. So 3 9 the 27. So 1 will be the remainder. So in slot 1, I will put 28. Similarly, you have to do. Similarly, you have to do. So what is 19 mod 9? Again, so 1. So 19 will also come here. So 19 also gets mapped here. So two things cannot be put here. So what we will do is we will form a chain. Okay. So in which slot we had 3 members, Gahan, three keys. Okay, slot 1. So what is the other number that will come to slot 1? Okay, so 10 is also there. So let's go to, so what is h of 10? H of 10 is 10 mod 9. That means remainder is 1. So again, this will also get mapped here. So I know for a fact that this one slot is getting 3 keys. So the maximum chain length is 3 or more. But as Gahan has calculated, oh, just tell me what are the numbers so that we can save time. So in 0th slot, there is anybody? Have you calculated? So anybody can tell if there is anybody in the 0th slot? Okay. One slot, there are 3 elements. Second slot, is there anybody? So 20 is here. Yes, because 20 mod 9 is 2. Third slot? Third slot, there is nobody. Is empty. Fourth slot. Fourth is also empty. Sixth. The fourth, there is okay. Fifth, there is anybody other than 5? Only 5. Okay. Sixth, 15 and 33. 15 and 33 are in sixth slot because 15 is 6 mod 9. 33 is also here. 33 is like 9, 7, the sorry, 3, 9, the 27 plus 5. That is fine. Seventh slot. Seventh slot, there is nobody. Eighth slot, 17. Yeah, because 17 mod 9 is, what is h of 17? 17 mod 9. Divide 17 by 9, you get 8 as remainder. So it will go there. So yeah. So I've put all the 9 numbers. 3 plus 1 plus 1 plus 2 plus 1. So 5, yeah. So this is the heaviest slot. So the maximum chain length is 3, not 4. So this is our correct answer. Correct answer is this. All right. Any doubts on this question? Yeah, Alok is also correct. So Alok had answered 33 for, I think, slot 6. That's correct. So we'll see one more question before the break. What is the worst case time complexity of the binary tree sort? So I'll give a minute to think about it. Worst case means like the for the most time consuming input, what is the running time? So always when you see that there's a sorting algorithm, if it happens to be a comparison based sorting algorithm, not like counting sort, if there is a comparison based sorting algorithm, then you know that it's not going to take less than n times. So this is anyway ruled out. So you've seen that in insertion sort, uh, when the numbers were already sorted, then we had to just make one comparison in each iteration and order n time was sufficient. But if you look at the worst case running time, the worst case running time of any comparison based sorting algorithm is at least order n log n. So this is also ruled out. So you have to either choose B or you have to choose C. So at least n log n. So it could be n log n or n squared. Okay. So there are multiple answers. Gahan is saying option C and Alok is saying option B. So first we'll see, is there anybody else having a different opinion? So let us take an example. Suppose this is the array that we want to sort. So how does binary tree sort work? Actually, it is supposed to be binary search tree sort. Okay, so what it does is it forms a binary tree. So what is the first step? So step one is construct a binary tree, or rather a binary search tree with the given input. What is the step two? Perform an in order traversal in this BST that you have constructed in step one, binary search tree. What is in order traversal? Anybody? Left root right. That is correct. So in order traversal means first you look at the left subtree. First is look at the left subtree, followed by the root, followed by the right subtree. This is called in order traversal. Okay. So now first let us see how we can perform step one on this input. Okay. So first is insert one. So there is no binary tree, an empty binary tree gets one. Okay. So we scan one, we have one. Then we scan the next number, we have two. So two is larger than one. So two will become a left child of one or right child of one. So two will be placed here or here, to the left or to the right, in a binary search tree. Okay, because in the right subtree, larger than one numbers will be there, and in the left subtree, less than equal to one numbers will be there. Okay, so two is larger than one, so two will come here. So the next we will see four. So we will see, okay, four is more than one, we go to two. So two will go to the right of four. Then we get seven, seven will go to the right of seven, four. Then we say we get five. So five, five, four, four to the left or to the right. So four should go where? Sorry, four is already done, no? Five. So five should go where in this tree? Left of seven. Okay. Yes. Okay. That is one way. And the other way is that, okay, so what is the height of this tree? So how many levels are in this tree? This is level 0, level 2. So there are 5 levels. Starting from 0, we come to level 4. Okay. So this is not a balanced binary, this is a skewed binary tree. Okay, so what we have seen in the classes that there is a concept of balanced binary tree, binary search tree, where the number of levels is minimized. So many levels are, it's like a path. We want to minimize the number of levels. So what is happening is, if the levels are so many, so there are n elements, in this case 5 elements, and there are 5 levels. So for every insertion, the cost is order. So in the ith iteration, insertion, for example, for the third insertion, I have to go till the third level. So for the ith insertion, I have to traverse I levels for ith insertion. So what is the total number of traversals? For insertion, total time that we will require. So for the first number, we had no time. Just put the number. In the second iteration, we had 2 times, and so on. For the fifth iteration, 5 times. So for the last iteration, if there are n numbers, we need so much time. So that what is the sum of the first n numbers? What is the sum of the first n natural numbers? N into n plus 1 by 2, not n minus 1. So this much time we will require, because in each iteration, for each insertion, we have to go so much down, I levels down. So in the first insertion, 1 second, 2, and so on till n. So much time is required. So n into n plus 1 by 2, that is order n square. So if the binary search tree, if it is not balanced, if it is skewed like this, then how much time we get? How much time is required? Order n squared. So therefore, in the worst case, this is the answer we'll give. Is that fine? So construction of the binary search tree will take so much time. After the in order, okay, how much time does in order traversal take in a binary search tree? So there is a binary search tree with n elements. Then how much time will this in order traversal will take? So you start at the root, then you check if there is a left thing or not. Then you go to the right. Then you, yeah, for in this case, you can say every node is getting traversed once. So in the worst case, every node can get traversed twice. So the running time is at most 2n. So it is order n. In order traversal takes order n time. But the step one, the construction itself has taken order n squared time. Construction of the binary search tree, as we have seen here. So we will choose this answer. Okay. Any doubts on this question? Okay, so it is 10 past 7. So we'll take a break now. So let us take a break. So let us take a break. So Resh will come back after 5 minutes and see the 3 other questions. So I think by 7:30 or so we'll be finished. Oh, it is 7:10, no? So we'll come back at 7:16. Yes. So welcome back. This is question 8 for today. So I'll give you a minute to think about it. Okay. So we have an answer. So Gahan is saying true. Why is it true? So let us explain the question a bit. So you have a hash table, but it is open addressed. So what is a hash table? It's an array. So you know that load factor is n by m. So there are m slots in the hash table. M slots in the hash table, and n keys are to be hashed or stored into this hash table. So what percentage of the hash table is filled? That is the load factor. It is n by m. For example, if the hash table size was 100 and 75 elements were to be filled, then alpha will be, the load factor will be how much? N by m, 0.75. So alpha is the load factor, that is what percentage of the hash table is filled. Are you with me? So you understood what is the load factor of the hash table, have you? Okay. So now at some point, when we are looking at the load factor is alpha. Okay. So n keys are already hashed here. When you increase, you hash more elements. So if you insert another element, so the load factor will increase or decrease. So load factor becomes n plus 1 by m. So that means the load factor is increasing. The percentage of the hash table being filled is getting more. Some more portion of the hash table is getting filled. So it is saying that, so the question is saying that when the moment when the load factor is alpha, you make, you try to make another insertion. So the expected number of probes in an unsuccessful search, not insertions, I was saying that we'll search for. So when in the hash table we can search also. So we search for some element which is not in the hash table. So unsuccessful search means that element is not present in the hash table. Okay. So what happens is, for example, that element we are looking for, let us say that element is k, then we compute hk and go to that part. So let us say hk is supposed to be here. and we see that uh, some other element is there. That element is not there. Multiple things can get mapped here, right? Then we will. So what happens in open addressed hashing is that you obtain HK, you go to that particular slot where K is mapped, and you see that your element K is not there. Then you check in the immediately next slot. So we check if K is present here. If it is not, then we check further. So the question is, how many times you have to check in case of an unsuccessful search? How many probes we have to make? That is the question. So is the question clear? Okay. So suppose alpha is 0.75. So that means 75% of the hash table is filled. So that means 25% is empty. 25. So if the number of slots is 100, then 75 slots are filled and 25 slots are empty. Suppose. Okay. And at that point, you perform this unsuccessful search. Okay. Then what is the expectation that, forget expectation. What is the probability that a particular slot is empty? So 25% slots are empty. So probability is 0.25. So the probability is 1 minus alpha. The alpha percentage, alpha portions of the slots are filled. So 1 minus alpha portion of the slots are empty. So that is the probability that a particular slot, any randomly selected slot, is I should not say particular, randomly selected. Slot is empty is 1 minus alpha. Okay. So that means if you come to an empty slot, you don't find anything, that in expectation, the reverse of that, the reciprocal of that, that is 1 minus 1 by alpha probes need to be made in expectation, because this search is unsuccessful. Okay, so that's how we get 1 minus alpha probes at the most. So what is expectation? It comes from the theory of probability. I think this has been discussed in the videos. Any doubts? Any questions? So what is a randomized binary search tree? So we know what is a binary search tree. A randomized binary search tree means, suppose you are given an array A. So in this case, they are saying that the array is 132. So you are given three numbers 132. So how? So if you want to make a this thing, uh, uh, binary search tree out of this, so one you place two, and then you place three, like this. Okay. So, but if you are talking about randomized binary search tree, then if first you take a random permutation of the input. So, for example, I took 213. Then what will I do? So, I'll do this 213. This will become the new binary tree. So, depending on what permutation you have taken, you will get a binary search tree, right? So, how many permutations of 132 exists? Yes. The three numbers, so 3 factorial 6 permutations are possible. Yes. So for the 6 uh, permutations, we'll get 6 binary search trees, but 6 is not there in the options. But the number is not more than 6, so we can definitely rule out 8. The number question is whether it is 4, 1, or 5. So it can happen that two of the permutations give rise to the same binary search tree. That can happen. Is it 5? Yes, it is 5. So we have to identify that which two permutations give rise to the same BST. That you have to identify. So I'll give you a minute to identify two distinct permutations for which the BST is identical. So for 213, yeah, we can draw all 6 BSTs. But I thought that he will do it. But anyway, I'll do it. This is all we'll get, right? Is this correct? Now you can tell me which two are identical. Yeah. So these two are identical. So you see there are five different ways we can form a BST. So the question is, how many randomized BSTs can be formed using the numbers 1, 3, 2? The answer is 5. Is there any doubt on this? Any questions? Any comments? All right. Can you have 3 in the right of 1? So for example, so in 2, 1, 3, first is we make 2 the root. Then you look at 1, 1 is to the left of 2. Then we have 3. So you will keep it here. So ideally, you would like to make it as balanced as possible. So that's how, to take care of balance, we'll put 3 here. Any other questions? So we have come to the last question of the day, the showstopper. So I'll give you 5 minutes to think about it. To think about it for 5 minutes. So I hope that you had a chance to think about it. So what do you think? Why why option B? Okay, just a guess. So first of all, uh, in the binary search tree, there are how many elements in total? We'll call it randomized binary search tree, RBST. With N. So how many of them are leaves in expectation? So of course, the total number of elements is N. So how can the answer be N squared? So N squared is ruled out. It's not possible. So you have to choose between the remaining three. Now, so how is the randomized binary search tree performed? So you are given this set of numbers. So you are given this set of numbers A1, A2 up to AN. You first obtain a random permutation of this n numbers, and then you construct a BST as per this permutation, while minimizing height or while keeping it balanced. I mean, as balanced as possible. So you are not doing rotations. You are just following the order of the permutation. So in the best case, so in the worst case, so for example, if it is very skewed, like if the numbers are all sorted, like we have seen in this, that if the numbers are all sorted, like 1 2 3, then we get a BST which is like this, very skewed. Height is 3. I mean, number of levels is 3. Sorted in reverse order, again, height is 3. So if the numbers are sorted up to n, then you will get something like this. So how many leaves are there? There's only one leaf, n guy. The guy n is the leaf. Everything else is an internal node, isn't it? So for a sorted permutation, we have a situation like this: 1 2 3, everything is internal node except one. So for a skewed tree, number of leaves is only one. Okay, but on the other extreme is what? For a balanced tree, what is the number of leaves? So suppose there are 15 elements. Number of leaves depends on height. Yes. So for 15 elements, you can see that there are 8 leaves. So in a balanced tree, if you assume that there are 2 to the n minus 1 kind of elements, so almost like about n by 2 leaves you will find. So balanced means minimum height. Okay. So balanced tree means minimum height. So if you want to minimize height, so you'll try to make a structure like this, and therefore the number of leaves is about n by 2. Okay, so the number of leaves is about n by 2 in a very balanced situation. In a skewed situation, the number of leaves is 1. So when you have randomized, then yeah, go ahead. Who is that?
Actually writing
Yes.
బయట బుక్కులు బయటనే లేస్తాను బయట కాదు మీ మామూలు సైన్ చేయాలి సన్నగా తెచ్చింది అది క్రాఫ్ట్ అయితే
Wow.
అది కాదు అంటే సరే దాని ఇంటికి వచ్చి
What are we talking about? What is Harshini talking about? Okay. So you have generated a random permutation. So if you have generated a random permutation, it is highly unlikely that you will get a skewed tree. So the number of leaves is being 1 is not very likely. So the probability of this happening is also very unlikely, and getting a balanced tree also is not very likely. So these were extreme cases because you have generated a random permutation. Okay. So 1 is also very unlikely, and n by 2 is also very unlikely. So something in between will be the answer. So from that, I will guess it is probably n by 3. So n plus 1 by 3 is almost like n by 3, isn't it? So I will rule out this because this is an extreme situation. And this is also like n by 3. N minus 3 by 2 is asymptotically, this is like n by 3 only approximately. So I'll also rule out this. So I'll go for this. But what is the exact way to get n plus 1 by 3 in probability? So professor has written that in a random mathematical model. So I'll just write down what professor has written. So there is a proof of it that why uh, uh, the expected number of leaves is n plus 1 by 3. I will just write down what the professor has written. Whoever is a course instructor, professor, I, I have to check anyway. So in a random, that's what he has written. Mathematical model, the expected number of leaves in a randomized binary search tree is exactly n plus 1 by 3 using probability. This is what he has written. No further explanation. But it is possible to prove it using probability, but I'm not able to do so right now. I have to find out how to do that. But the intuition is this, that in one extreme you have number of leaves is 1, other extreme is number of leaves is n by 2. So something between these two. So n by 3 is much less than n by 2, but it is much more than 1. So that's why I'm going for n by 3, n plus 1 by 3. But there is a way to get the exact number using probability. That's what the professor has written. All right. Any questions? So this was present in the last video. Okay. I don't know. I have not watched the videos. Does somebody know whether this was discussed? Randomized one research tree, expected number of leaves in the videos. So this is the okay. So I'll take a brighter color. So this is the end of session for today. If you have questions, you can ask me. But officially, the session has ended. Okay. So you know the runtime of the randomized PST sort. Okay, that is great. In question number 8, a theorem was given for an unsuccessful search. Yeah. Yes. What is the question? Okay. So which part of the proof you did not understand in the lecture video? The proof led to 1 plus alpha square plus dot dot dot. Oh, I think this is the. Let me try to write what you have written. So you are saying that there was an occasion in the proof where you had 1 plus alpha square and so on, and this was replaced by 1 by 1 minus alpha. Is it what you're talking about? So this is called a GP. So this is a geometric progression. It's an infinite GP. Yes, Nitish is right. So it's an infinite GP because the number of terms is infinite. And what is the common ratio? Common ratio means the ratio of two consecutive terms. For example, alpha by 1, that is alpha. So is alpha less than 1? Yes. So in that case, this is the formula. So for example, if this is the GP, rather I would put it a slightly general way. So let us say first term is A, and then R is the common ratio. Then A by 1 minus R is the formula for uh, this infinite GP. In this case, A is 1 and R is alpha. But you can also do it from the scratch. For example, how to do this, I'm telling you. So you can write this as, so take alpha common second term onwards. So you are going to get this thing. So you've taken alpha common second term onwards. Here we have taken alpha, so we get 1. Here we have taken alpha, so we get alpha. So what is this part? This part is again nothing but what you started with. Let us say I call it S. So this is the series itself. So this is 1 plus alpha S. So S is equal to 1 plus alpha S. So S 1 minus alpha is 1. So S is 1 by 1 minus alpha. So that's how you can get. You understand? Okay. So you remember that alpha should be less than 1. Otherwise, this does not work, because if alpha is greater than equal to 1, so if alpha is greater than equal to 1, then this term will become less than equal to 0. So on the left hand side, we will have a negative term. On the right hand side, you have 1. So we will face an contradiction. So therefore, alpha should be less than equal to 1 for this to hold. Is there any other question? Anything else? So thank you everyone for joining. We are out of time. I'll see you next week. Good night. This fundamental algorithm is much harder than the Python classes. So you are going to the Python classes also? You mean you were there in the yesterday session? Okay. Yeah, I mean, this is the first course in algorithms, whereas Python is more implementation based. This is more theoretical, more mathematical learning, so it is much harder. You're right. But it will improve your analytical skills, how to analyze algorithms, how to think about algorithms, which is a basic skill in computer science. So I think it is going to add value to your knowledge. And also it's a 4 weeks course, so it will get over quickly. So I think you'll learn something out of it if you are consistent. Okay. Okay. Thanks a lot. Thank you for joining.